Okay, hi everybody. Thank you for the good introduction and for the invitation to speak here. It's been really inspiring to see how here at Rick and you guys are really thinking about combining the supercomputers and the quantum computers. I think that's going to have a lot of very good science in the future. So I'm Roland Farrell. I'm a postdoc at Caltech, and today I'll be telling you about progress on doing simulations of scattering using quantum computers. My background is in nuclear and particle physics, and the kind of problems that I get really excited about is related to what happens in a higher energy collision between heavy nuclei. So we have these particle accelerators, such as they have at the LHC, where they collide two lead nuclei at close to the speed of light. And it turns out that when you collide things at very high energy, you have these neutrons and protons that completely burst apart, and you're left with this liquid called this quark-gluon plasma composed of the actual fundamental building blocks of these neutrons and protons, the quarks and the gluons. And as this quark-gluon plasma cools, then it expands and reaches a sort of thermal equilibrium. And what you measure in your detectors in these kind of experiments are, again, these neutrons and protons and other hadrons. And in any of these kind of experiments, we know what our initial state is, what nuclei we're colliding, what energy we're colliding them at, and we can tell what we've measured in our detectors, but we have to do a lot of kind of uncontrolled inference to probe that in-between region. How do these neutrons and protons break apart? How does this quark-gluon plasma form? How does it cool? All of these are very open questions that we would like to know about. And to really get at these in a quantitative way, we need to simulate the underlying quantum field theory. So particle physics and the standard model of particle physics is described by quantum field theory. And in principle, this gives us the equations we need to solve in order to figure out what's going on in these kinds of high energy collisions. But of course, these kinds of simulations are extremely difficult. These simulations using classical computers have been successful in a lot of arenas, but one of the places where they start to struggle is in simulations of real-time dynamics, where you want to know what happens as a function of time. And this is the area where we believe that quantum simulation on quantum computers can provide an exponential speedup. And so this is a motivation for trying to simulate these kind of processes on a quantum computer. So right now, the state of the art in doing these scattering simulations is, of course, using classical computers and using what are called these tensor network techniques, in this case based on matrix product states. So I've shown a couple of examples here from the literature. These are works done in the last year where they're trying to do these simulations of scattering. What these pictures show is on the horizontal axis, this is the spatial direction. On the vertical axis, it's the time direction. And it's showing the initial preparation of two wave packets of particles that have equal and opposite momentum, that then as they evolve forward in time, they come together and collide. And what's very exciting about these simulations is you can see that there's a bunch of different behavior that occurs as you increase the energy of the collision. So this is showing from left to right, increasing energy. So for low energy, you get what's called elastic scattering, where two particles come in, and then they interact, and then two particles go out, and they kind of form this X-type shape on the space-time diagram. But as you increase the energy, you can start probing non-perturbative aspects of your theory. This is showing what happens if you scatter very close to the energy of a resonance. Resonance is like an unstable bound state, and you can see that you get this lump of energy that sits around in the middle of your simulation and then slowly decays. And this is another type of scattering where you have two light particles scattering and actually forming two heavy particles. And so it's very, very inspiring that we can actually begin to see information about aspects of our theory, bound states and resonances, directly from performing these real-time simulations. And I should mention that there's been similar work in other theories. This is showing a U1 lattice gauge theory or electromagnetism. But of course, these are great. The limitation is that these MPS methods fail when you want to try to do simulations beyond one dimension. And of course, the real world is 3 dimensions. That's where we eventually want to go in order to have realistic simulations of quantum field theories. And so we need something better in order to get there. And that's where we believe the quantum computers will come in. So this is kind of a summary of the state of the art simulating these scattering processes on quantum computers. So right now it's kind of just in the beginning phases of this, but already there's been some remarkable demonstrations. So this top left is showing the preparation of one of these wave packets on a quantum computer. This is done on Quantinuum H1. This figure up on the right is some work that I was a part of where we prepared one of these wave packets and then time evolved it. And this is in using IBM's device, IBM Torino. And then similarly, there's been some very early demonstrations of scattering where they actually prepare 2 of these wave packets of particles and smash them together. And so it's very nice to see that these demonstrations are now possible. But, oh yeah, okay. I want to highlight, it's my work. So this simulation for the latest time required close to 14,000 2-qubit gates. And so for me, this is very inspiring because we're entering this regime of quantum utility where the circuits we can run and get meaningful results are quite deep, and we expect to soon be able to do things on the quantum computer that we cannot do on the classical computer. So these are very great, but a serious limitation for doing these kind of simulations is this state preparation. So how do you prepare this initial state, which you then want to evolve forward in time? And this is a problem that I'm going to kind of address in the talk today and provide one sort of solution for this. So it's important to remember that we're in this NISQ era of quantum computing where our devices are noisy, and right now we can expect to get reasonable results off of circuits that have a 2-qubit gate depth of around 100, maybe a couple hundred, but if we have depths of 1,000 and beyond, we are going to have too much noise, and we need to wait until we have fault tolerance really to get to this region of 1 billion or 10 billion circuit depth where we can expect to use a lot of the hallmark quantum algorithms like quantum phase estimation or block encoding. So for the time being and for the current future, I think it's really important to think about how do we leverage the full capabilities of classical computing to really reduce the depths of the circuits we want to run on the quantum computer. And so the focus of this talk is going to be how we can find these very shallow circuits that implement state preparation, in this case for a scattering experiment. So in a scattering simulation, you start with 2 of these wave packets of particles that are far away, and this state actually has quite low entanglement. And then as you evolve it forward in time, these wave packets move closer to each other, the entanglement stays pretty low, and then once they start to overlap and you actually have this collision, your entanglement starts to grow exponentially in time, and if these collision was energetic enough, you would expect to have enough entanglement that really all classical methods would start to break down. But the very nice thing is that this initial state actually does not have a lot of entanglement. And this kind of means that we expect to be able to simulate it efficiently using these tensor networks or matrix product state methods. So the idea that I'm going to propose is, are we able to find these shallow state preparation circuits using quantum variational algorithms run on classical computers? And what's very nice about these variational algorithms is they find very shallow circuits for doing your state preparation task. And in the remaining part of this talk, I'll tell you about one way that I've worked on to map this wave packet preparation problem onto an optimization problem where then we can perform these kind of variational algorithms. So to start with, I want to consider a very simple field theory, arguably the simplest one you could come up with, which is Ising field theory. So the Hamiltonian is given by a very simple model that we're probably all familiar with, the Ising model, on a one-dimensional lattice with periodic boundary conditions. And it turns out that as you tune this, this model to criticality, where the correlation length becomes very large, so you take this transverse field strength to be 1 and this longitudinal field strength to be 0, that you actually get a field theory. And there's a whole family of field theories that you can tune to depending on the ratio of this combination of parameters here. So this family of field theories is called the Ising field theory. In this field theory, you have single particle eigenstates, which are plane waves. They're labeled by some momentum quantum number k, which we'll call psi k. And from these plane waves, you can construct these localized single particle wave packets, essentially by adding together a bunch of these plane waves with some kind of Gaussian profile. This makes a wave packet that's centered around some momentum k. So this is the object that you can form that moves kind of as a coherent single particle with some specified momentum. So the goal is try to prepare this kind of state on the quantum computer. But already, just from looking at this, you could see why this kind of state preparation could be difficult. Here we have a sum of eigenstates with different weights, these psi k's. We know we have these variational algorithms to prepare a single eigenstate, but adding different eigenstates together is difficult for the quantum computer, mostly because addition is difficult on a quantum computer. So there's some proposals using linear combination of unitaries to achieve this. These kind of work well in the asymptotic regime of a very, very noiseless quantum computer, but in practice, they require very deep circuit depths. So to gain some progress, I want to start with an even simpler problem, which is consider setting the transverse field strength to be 0. So here your Hamiltonian is just diagonal, very simple. You can write down what these single particle eigenstates are. They're just superpositions of the state where everything is spin up except for one spin, which is spin down, and the location of that spin down is added together with a different phase specified like this. So it's just a plane wave where one spin is flipped. And then from these, you can form the corresponding wave packet in this simple theory that I'll call this psi 0 wave packet. And what's nice is because this Hamiltonian is so simple, it's quite easy to find a circuit that prepares this wave packet. So if you look at the wave function for this wave packet, it's this Gaussian where at every different site you have the location of this one spin down, and the amplitude has this Gaussian profile. It has a similar structure as the W state in quantum information science, which has been well studied. And it turns out you can prepare this state with a constant depth circuit using measurement and feed forward. So this is a state which we can prepare efficiently. Now the question is, does that really get us anywhere? So the challenge is there a unitary which would take us from this easy to prepare state, the psi 0 wave packet, to the actual wave packet that we want and we can use in our scattering simulation? To make some progress, there's a couple observations I want to make. So if you look at the Hamiltonian, because we have this translational symmetry, we know that it's block diagonal in the momentum basis. So you can block diagonalize it with different blocks corresponding to different momentum values. And these single particle eigenstates, these psi k's, are the ground state in each one of these corresponding k blocks. So it's the lowest energy state with some momentum, except for the case where k is 0, in which case that's just the actual ground state of the complete system. So that's one observation. The second observation is that the state that we're able to prepare easily, the psi 0 wave packet, has the correct amplitude in each k block. So the amplitude is correct in each one of these momentum sectors. The problem is that it's spread over every single state with that momentum quantum number. And so what we want to be able to do is project each one of these k blocks onto the ground state. If we can do that, then we'll actually have the wave packet that we want. And so now you can see that, okay, we want to project to the ground state. Maybe we can frame this now as some kind of energy minimization problem. And indeed, that's what you can do. So it turns out that this unitary that prepares this wave packet state can be found by doing this variational algorithm where you're minimizing the energy with some unitary operation or some circuit that depends on parameters theta, where you're starting from this easy to prepare psi 0 wave packet state. And if you can minimize this energy, that's how you find this unitary operator here. The one thing is that your unitary is subject to two constraints. So the first one is that it must be translation invariant, which means if I, say, pick up the circuit implementation of that unitary and translate it by 1 unit, the circuit should remain the same. And it turns out it also needs to be an orthogonal matrix or a real unitary. But what's really nice is that these symmetries actually simplify the optimization process tremendously. They really constrain the kind of structure of circuits that you can search over and make a lot of the problems associated with barren plateaus and other problems with the optimization of quantum circuits not really manifest. So specifically, the way that this works is that you have a circuit for preparing this psi 0 wave packet. You have another one to minimize the energy and optimize these parameters. And by doing this whole process, you get out your unitary. And so the way that I've been doing this is by minimizing the energy using this adapt VQE protocol. It's a variant of VQE. And using an MPS simulator on 100 plus qubits, in particular the QUIMB MPS simulator. So this is great. This gives us the circuit we need to prepare this initial wave packet state. It's very shallow, and so it's now amenable to being executed on a quantum computer. And this has all kind of been verified by actually simulating all the circuits that you need for doing this scattering simulation, so the initial state preparation and the time evolution. This is showing this plot for the Ising field theory. It turns out this method is actually quite general and works in many different field theories and also in more than one dimension. And so it's also been tested in this lambda 5/4 scalar field theory. And what's quite exciting is that the number of qubits and circuit depth that you need to simulate the scattering is really not too great. So in this Ising field theory case, it seems that with 100 qubits and a depth of about 150, assuming linear connectivity, that you can perform this full simulation. And for this scalar field theory, if you had 54 qubits and around a depth of 350 with all connectivity, you could simulate scattering in this theory. And what's very encouraging is actually there's been work here at Riken exactly in this same model, this tilted field Ising model. In their case, they were looking at these discrete time crystals, but they were able to simulate depths of 300 on IBM Torino. And so I'm very optimistic that a depth of 150 or something comparable to that can be simulated with decent fidelity. So yeah, the next step is to take these circuits and execute them on the quantum computers. So I'm currently waiting to have access to the quantum computers of IBM and Quantinuum, but it seems very likely that these simulations can proceed. So yeah. So yeah, with that I would like to summarize the talk and provide a brief outlook. So I presented a new method for preparing this initial state in a quantum simulation of scattering. The key thing is to have a variational optimization that's run on classical computers. This is really nice because it determines shallow state preparation circuits that are then can be executed on the quantum computer. And then the quantum computer is doing the more difficult thing of simulating time evolution, which is really what generates the entanglement in the process. And it seems very encouraging and optimistic that this will enable simulations of scattering that are going to go beyond what's possible with classical computing and really give us a new angle into these quantum field theories that we've studied for a long time. So of course, a question we should ask ourselves is, can a NISQ quantum computer or a near-term quantum computer provide a quantum advantage in a simulation of scattering? And I think the answer is probably not in 1D scattering. These matrix product state methods are really good, and even though in principle the entanglement can grow exponentially over some time window of scattering, it seems to really enter the regime where that starts to break down and is quite difficult. So I think In 1D scattering, we won't be able to get a quantum advantage, but that will change completely once we go to 2D and higher dimensions, because there all of these classical computing techniques break down, but the method on the quantum computer remains essentially the same. The circuit depths are more or less the same, and so it seems we could very easily simulate scattering in beyond one dimension that would be impossible with any classical computing method. So with that, I would like to thank my funding. So my funding is from the Burke Institute at Caltech. I'd like to thank the people who have advised me and worked on me with this project, my advisor, John Preskill, and my collaborator, Nikita Zemlevsky at University of Washington. And I'd like to thank you all for listening and be happy to take any questions. Thank you.